In this video I'm going to talk about Ampere's law. So this video essentially will supplement the video series I made on magnetism. Ampère was French, like many other people working on electromagnetism at the time. And when you write out his name, right, he's got an accent grave up here. It's like this way, not this way, and it's above this E, not that E, right? So it means his name is Ampère, not Okay, beside the point. So of course the same Ampère after whom the amp is named, so like the Ampère, the unit of current. So Ampere's law is sort of a little bit like Gauss's law in terms of how it's used, how you might think of it. It is not Gauss's law for magnetism. That's something else. Let me write this down actually. So Gauss's law for magnetism but note, there is a Gauss's law for magnetism that is not Ampere's law, and that essentially says that there are no magnetic monopoles. So Gauss's law for magnetism is that the area integral of a closed surface, much like Gauss's law for electrostatics, B dot dA. So just replace the E in Gauss's law for an electric field by magnetic field. And it is not something times the charge inside, because there's no magnetic charge. It's kind of the point of the law, 0, right? So this is something else. This is in a way also very, very sort of fundamental and very interesting philosophically, but this is not what Ampere's law is. Ampere's law is something distinct. So this one here we're probably never going to really need, because all this really says is that it says that there are no magnetic charges, right? And one consequence is that it says that magnetic field lines will never end. They don't end on charges because there are no magnetic charges. But that is an aside. Let's talk about Ampere's law proper. So it's a bit like Gauss's law and how it's used. And it is one of the fundamental sort of cornerstone, fundamental pillars of electromagnetism. The others, are Gauss's law for magnetism, and what's called Faraday's law. And we're going to come to that last one later. So, primarily in this video, I'm going to talk about how we can use Ampere's law in order to do calculations. And much like when we had Gauss's law in electrostatics, what we did with it was we calculated the electric field for certain symmetric setups. And we did it essentially without doing any real integration. Right? There was an integral in Gauss's law, but we always picked these nice surfaces that match the symmetry of the setup, like a spherical Gaussian surface for a spherically symmetric setup, a cylindrical Gaussian surface for cylinders and long straight cables, essentially, right? It's the kind of idea we're going to employ here too. And then we're going to be able to find the magnetic field in the same way. But let's first see what the law actually states. So the law is this here, right? This is Ampere's law. It says that a line integral, and I'll talk about what that is. So this whole thing here is the line integral. Explain that in just a second. Of the magnetic field around a loop, and we walk around this loop in tiny steps that we're going to call ds. That integral, all said and done, comes to be equal to mu naught, that constant that you know from the Biot-Savart law, for example, and that determines the overall strength of magnetic interactions, times the current through the loop, right? So with a loop, you can't enclose anything inside because it's just a loop. Here's a visualization of this. Imagine I've got some currents flowing, maybe 2 cables, could be 3, could be 1, could be some kind of not well-defined cable at all, but just electrons sort of streaming through this. Doesn't matter what, as long as there's charges passing through this this loop. The green one is my Amperian loop. As long as there are charges going through it, has a current going through it, and what it says is the line integral evaluated along this path here, all the way around, end up where you started, that line integral comes to be 0. Sorry, not 0. Comes to be the mu naught times the current through the loop. 0 if there is no current going through the loop. That's what the law states. So, two things we now have to cover is how do line integrals work, and I talked about it a little bit too in the homework preview for chapter 29, but I'm going to go through it here again so we can make sense of it. And then we're going to see some examples of why is this law actually useful in the first place. And that's our goal. Alright. So line integrals. Of course, this is not a course on line integrals, so we're not going to actually evaluate a lot of complicated line integrals. We're not going to evaluate any complicated line integrals. We only do very simple ones. So let's say I have some kind of shape here. This is my path. My path has an initial point and a final point. So when you have a line integral or a path integral, we also call this path integrals. It's another name for the same thing. I am summing up something which is an integral. Integral means taking an infinite sum of infinitely tiny little bits, taking tiny little steps along this path, and we're evaluating quantity for every step. And let's imagine there's some magnetic field here. And let's say, to keep our lives somewhat simple, the magnetic field is always pointing straight upwards. Right, so wherever we go, it's straight up. Of course, it doesn't have to be that way, but I think it'll just make our life a little bit simpler. So what do you imagine I do when I'm going to evaluate the line integral B, that's my B field, dot ds. What is this? So this thing means, so this is for a loop. In our case, I don't have a loop. I have just a normal integral without the loop sign. So the loop sign means I start and end at the same spot. That was the example here. Imagine if I start here, I walk around the loop, but I end up where I start. My initial point is my final point. Right? Now, the path you take from initial to final is going to matter in general. This particular example, actually, if you work it out, it might not. But, in general, the path you take, this line integral along this path is going to give you one number. Line integral along a different path, maybe like this, is going to give you a different number. So let's say I want to evaluate this integral, and I start at I and I end at f. So this is what this means, right? It means take the sum of, and I'm doing this along this path. Take the sum. So really, I should say, okay, being a bit inconsistent here. Let's just say along the path, right? Because from I to f, it doesn't tell me what shape. So by path, I mean, well, this path here. This is my path, right? The drawn path. That's along which we're going to take our integral. From I to f, true, but if I just define the beginning and end point, then I wouldn't tell the whole story, right? There were many ways to get from I to f. It could be going this way. Right, so that's why I'm changing my notation here to actually write, look, you have to integrate along this given path. Okay. So b dot ds, what is this saying? It's saying take the sum of all the tiny b dot ds for each step ds So when we take the sum, of course what we mean, because integral, we mean we take the infinite sum of infinitely many parts, infinitely many terms in our sum, of all the tiny, and by tiny, of course, we mean technically infinitesimally tiny. But of course, I can't draw this, right? So I'm going to pretend I'm taking tiny steps from here. So I'm going to here, then ds, 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 like one step after another. So let's just focus on some of the early part of this path that we make this a bit bigger. So this is the path at the beginning. This is where we start. Here's my point I, and then it keeps going. So I'm splitting my path into tiny little steps. Here we go, here we go, here we go, here we go. Right? So you can imagine sort of doing it like this. Of course, as I said up here, right, technically each step should be infinitesimally small. We're going to shrinking it down to essentially zero size. That's how I need an infinite number of them to actually make it to the end. But I'm going to draw it like this so we can visualize what's going on. So each one has a certain length, right? So let's pick one here, ds. Right. Each one is a little ds. Then I've got a magnetic field, and at this point here, where this one, the one I'm talking about right now, is, the magnetic field looks like this. So I can evaluate just the dot product of those two vectors, right? B dot ds. Let's count. 1, 2, 3, 4. So this is ds4. This is the fourth one. B dot ds4 is equal, and I mean the B at that point, right? ds4 is, well, you work it out, it's B times the length of this times the dot product, cosine of the angle between them. You can imagine doing this for every step, right? The magnetic field in our simple example is always the same direction, but in general it might vary. It might be different here to here to here. So every time we'd work out what is B dot ds. Now, of course, you can't actually do this an infinite number of times. It never get done. So you can evaluate techniques for evaluating that if, for example, you have a given function that describes the curve and a function of what the magnetic field actually is in space, a function of x, y, and z. We're going to worry about situations where our setup is suitably symmetric that the B dot ds is the same for every single step. Right? So really that the B dot ds4 is the B dot ds3, the B dot ds2, the B dot ds1. So that means I'll be able to then sum up this infinite number of terms because every single one of those terms is the same. That's the idea. That's what we're going to do. Alright. So let's just apply this. Let's do some actual examples so we can actually see this law in action. Right? So we're going to apply Ampere's law like the way it's written here. And you're going to see how those line integrals work in that case. Alright, let's do this. So the first example, example 1, is just a straight wire. Of course, the wire has to be carrying a current, otherwise everything is zero. No magnetic field. Let me draw a wire. I pretend the wire is infinitely long, or at least very long, so it keeps going. Here's my wire. And now we're not going to start like from nothing, from scratch. We kind of know what the field looks like, right? So from the symmetry of it, let's say the current goes this way, we know that the magnetic field points around it like this. And around it like this. Right, of course, it all the further out, right? Use the curly hand rule for that. So we are going to pick a path, an Amperian path, that is just one of those loops. Right? So we want to find the magnetic field at distance r from the wire. Find the strength of B. So you know the direction from the curly handle. We're going to say we find the magnitude of B, the strength of B, at distance r from the wire. That's our goal. So we're going to pick a loop that is one of those that just goes along the same field line. So if this one here is, say I want to know it at a small distance, let me take this loop here. I'm going to trace it along it again, and say I'm going to make this my Amperian loop. Amperian loop. So I'm choosing my loop to go along one of the field lines. So I'm choosing this, why? Because it matches the symmetry of the setup, right? This is a circle, which is a loop. The circle is this wire. If I imagine this is my wire and I spin it like this, right, then it doesn't change the setup at all. Nothing changes. Similarly, this shape looks the same from all directions. So if you spin your wire like this and you spin your loop with it, again the loop doesn't change the way it looks. So this is how we match the symmetry of the wire with a single loop, right? Like if I pick like a triangle that would a triangular path around it, that would no longer be true, because sometimes you might be facing a corner, sometimes you'd be facing a side. It wouldn't be symmetric along a field line, and not just that, it also matches the symmetry of the wire, the field we expect for the wire. Right? So let's zoom in on my Amperian path here. So my path looks something like this. Right. Actually, let me draw this again. Let me draw it from the top view. Ignore this. Top view. So from the top view, I mean like looking down on the wire as if the current was coming towards us. Current's coming towards us. This is my wire. And then my magnetic field, this r away, is gonna go around like this. I'm gonna assume the distance from the center is r. So now my Amperian loop takes me along this field line. And this is my line integral here. It's gonna go all the way around. And this is kind of what I drew here in 3D. Now we look at it from above. This takes me all the way around. My little steps, ds. Right? All the way around the wire loop. Now, because of the symmetry, the strength of B is the same everywhere along the loop. Right? So this matches the symmetry of the wire, the point being that B is constant along the loop, our Amperian loop that we've chosen, and the angle between B and my path, or in other words, each step, is constant. Here the angle is 0. Okay, let's make sure we understand this. the field then goes like this. So if you're down, say let's take this point here. Right here, the magnetic field points down. The path is, because the path is just along the field line, the angle between the path and the field line is always 0, because you chose your path to exactly go along that field line. So at this point here, I get that B dot ds is just B, the magnitude of it, times the step size, times the cosine of 0 degrees. Of course, this is just 1, and so the integrand here, the B dot ds, is just the magnetic field strength times ds, the length of it, right? Okay, so that same logic is true for every single step. So around this loop, B dot ds is equal to the strength of B times the length of each step, but B is constant. B is the same everywhere along the loop, so I can take it out of the integral. So what I'm really just summing up is B times the step length. Summing up the length of each step, right, length of each step around the loop, I'm just going to get the size of the loop. The size of the loop is 2 pi r. Right. So the logic was I pick my loop in such a way that that in this case my path is exactly along a field line. That means every step, the angle between my step and my magnetic field is 0. Right? This is different from the case that we have drawn here, where I was stepping in a direction that wasn't in the direction of the field. There was an angle that was not 0. But we are stepping exactly along the magnetic field, which in the case of a wire, from the symmetry of it, means you must be going in a circle. And that means I can evaluate this for any single step. When I then take the sum of them, meaning the integral, then I can evaluate this here, but the B is constant because I'm the same distance from the wire each time, and if I imagine to spin this wire around, nothing changes, which means that the magnetic field can't have a different strength here than here. It would break the symmetry of the setup. So I can take the B out. Then this integral here is just this path length, because I'm just summing the individual length of each step all the way around. That is just the total length all the way around. All right. Are we nearly done? Yes, we are. So our result was the left-hand side of LHS of Ampere's law, A's law. Therefore, in this case, worked out to be the unknown field strength, right? We don't know that, times 2 pi r. Meanwhile, the right-hand side, that's usually the easier one, right-hand side of Ampere's law is mu naught, the constant times the current go through it. The current go through it we just called I, whatever the current is, the single wire. The mu naught I of the wire. So those two are equal. So I get that B times 2 pi r is mu naught I, and so my field strength B is mu naught I over 2 pi r, which you hopefully recognize by now as indeed the equation for the magnetic field strength at a distance r from the wire. Now proved using Ampere's law. We could prove it before and with essentially integrating the Biot-Savart law, but that's cumbersome and long. This is in a sense much faster. I went through it really in really slow steps, but it's a very fast calculation because we don't actually have to evaluate any integral. Alright, let's look at a different example. So this was a very simple one. And much like in case of Gauss's law, there aren't that many different types of symmetry that you could consider. Let me consider the following. Let me consider a sheet of flowing charge. It's kind of a river of charge. And the way I'm going to visualize this is as follows. Let me first write down the example. I'm going to call it a river of charge. So here's what that is. I imagine I have a big metal sheet. It's really long, something like this. But it's not very thick. And I imagine that it's really wide, really long, and current just flows this way. Right? So I can imagine there's a certain amount of current per meter. Like current, I can find out current per meter. It's kind of a linear current density. Right? So say this whole thing is 2 meters wide and I've got 5 amps coming down, then I'd have 2.5 amps per meter. Not sure what the symbol is. Usually we use symbol J for current density, but say current density not per meter. I'm gonna call it the current density. The linear current density. How much current per meter of sheet? Right, so the current just goes this way down. So that's why I say it's like a river of charge. It's like this is the width of the river and it's flowing down, and the same everywhere. So I'm just going to call this the total current divided by the width of the sheet. Call the width W for width. So I want to know what is the magnetic field close to the surface. Excuse me. Find B close to surface. So here's how we're going to visualize it. Let's imagine we look at it from the front. Let's look at it from the front view. I mean, we imagine we look at it from this angle here. So it's sort of like we look at it like, here's my eyeball, look at it from this side. So what do I see? I see essentially the edge of the sheet, and I see current coming towards me. So I'm going to draw it like this, as if it were a whole bunch of tiny little wires sort of stacked next to each other. That's the visualization. You can actually think of this as lots of wires next to each other, current going the same direction, sort of like this. So I want to find the magnetic field here. So find B here. Okay, how are we going to do this? So by the curly hand rule, the curly hand rule is for like a single wire, but I could imagine I apply the curly hand rule to every one of those. What I'm going to get is that this one's going to produce a field that's like this. This one's going to produce a field like this. A field like this, this. Right? Now, you notice that in between those, like inside the sheet, one goes up, one goes down. The effect essentially cancels out. Unless you're right at the edge where there's no further one coming, the magnetic field inside the sheet is essentially nothing. Imagine it's an infinitely thin sheet. So there's no vertical component. But down below, the field adds, it's always pointing this way. Above, the field is always pointing this way. Make sure you understand this, right? Why is it that the field down here, therefore, essentially points to the right, up here it points to the left, but there's no vertical component, right? This one going a bit up, cancelled by this one going a bit down. This one going straight up in between, this one coming straight down in between. So there's always this cancellation in the vertical direction. So our magnetic field just from that, it's going to be in this way direction down here, in this direction up there. So let's pick our loop. So now we understood what the direction of the field is just from the symmetry of the setup. I'm going to pick my loop to be essentially along a sort of square like this. Let me draw this again, so I don't make my diagram too messy. Here's the front view again, same thing, right here my individual imagined wires that make up this river of charge. The magnetic field up here is in that direction. The magnetic field down here is in that direction. So I am going to pick my loop to match this. So my loop is going to be, it's not going to be infinitely long, but I'm going to do it like this. Make this my loop. So notice it has corners, right? That's okay. And with the Gaussian surfaces, we also sometimes had like edges and corners, as long as it's closed. So it's sort of like I have this window, right? And I look through it and I see part of the current coming towards me through the window. That is my Amperian loop. And the blue line is, of course, the magnetic field. So by the symmetry, the magnetic field up here, the strength here is the same as here, because if I were to just flip the whole thing over, like, it wouldn't change the setup at all. B, the same, not the same direction, but its magnitude is the same above and below. Alright. So, and the direction is, as shown. It's like this, and down here, and there. It's like that. Oops. So like this. Okay. So, let's figure out what is b.ds. Let's label our sides 1, 2, 3, 4. So, for 1, b.ds, well, that is simple enough. The field is in the direction of the path is in the direction of the field. So that's just b times ds times the cosine, and write out cosine 0. So that's just 1. b.ds. The length of b, the strength of b times the length of my step. So what it means is my integral along path 1 of b.ds. Notice I'm not putting a little loop here, because going from here to here is not a loop. I start and end at different points. I only get the loop by summing the 4 paths. It's going to be b, so the integral, the sum along the path, b times ds, but b is constant, so that is just going to be the strength b times, well, if we pick how long do I make my loop, let's say this distance that I pick is L times L, right? Because I take the b out just as before, and the sum of the step sizes from here to here just gives me the total length of this. Okay, then what about number 2? For 2, I have that b is perpendicular to ds, right? I'm stepping down this way. The b field is to the left. So that implies that b dot ds is equal to 0. Because the cosine of 90 of this angle here is 0 for every single step that I take going down here. Now, for number 3, 3 is essentially the same as 1, just on the other side. So I'm going to get that third one, what am I doing? b.ds is equal to B times L. The left-hand side of Ampere's law for this part of the path is equal to just the magnetic field strength times L. And then 4 is again 0. Because again the path is perpendicular to the direction of the field. So what do we get? We get that the left-hand side of Ampere's law is equal to, it's this, around the loop, which is the same as taking 1 B dot ds plus 2 B dot ds plus the third part B dot ds plus the fourth part B dot ds, right? Hopefully you can see why this is, because those four paths together make the loop. So if I sum over the whole loop, it's the same as summing along the first path, adding to it the sum along the second path, adding to it the sum along the third path, adding the sum along the fourth path, because those four paths together, 1, 2, 3, 4, make up the loop. Okay, now I know what this is. This is going to be the magnetic field strength times L plus 0 times magnetic field strength times L plus 0, or 2 times this, right? But it only works because the magnetic field strength is constant along my path, or it's for 2 and 4 it's perpendicular to my step, so the angle creates a cosine of 90, which makes 0 here. So again, I was able to work out this integral without actually ever working out an integral. Now the right-hand side of Ampere's law is, well, mu naught times the current inside. Now if you think, what's the current inside my loop? So the whole current I called I. Really just rephrase this to I total down the sheet. This is used I to sort of symbolize the current is going this way. The total current down the sheet, I total. So the current inside that goes through here is essentially what fraction of the total sheet length is L. If L, length of the loop, is half the width, then it's going to be half the total current that goes through it. If it's a tenth of the width, it's a tenth of the total current. If L is, 1/100th the length of the width of the sheet, then the current through it is 1/100th of the total current along the sheet. So I'm going to write this as mu naught times L over the width of the sheet. W was the total width of the sheet times the total current. And I could say I total over W was my current linear current density. So I said mu naught times L times my linear current density. So now we set those equal, right? Left hand side equals right hand side. Sounds obvious because it's an equation, but sometimes you do a long calculation, you lose track of what you're doing. So I had this is this times the linear current density, for which there is, I think, no official symbol, and I don't feel creative enough to make one up right now. You can tell that the L's cancel out, which is good, because our loop, L was our choice, right? We made a choice, how long should we make our loop. We imagined our loop to be this. We could have chosen a wider one or a more narrow one. It was up to us. So if it was up to us, it better not affect our answer, right? It better cancel out. So what we get is that B, field strength, is just mu naught over 2 times the linear current density. Or in other words, mu naught over 2 times the total current divided by the width of your river of charge. Let's do one more example. I know it's kind of a lengthy video, but it's one of those big topics. At least I'm going to stick with one video in the case of Ampere's law, not make 5 like I did for Gauss's law. The last example, example 3, is the solenoid. It's kind of a bit of a funny one because in this case it's not really there's a symmetry there in the same way as in the others, and we make some approximations. So, what is a solenoid? A solenoid is essentially a sort of a spiral of wire, and it's always hard to draw in 3D. Let me see if I can do this. Does this look about right? Not entirely sure. So let me draw it like this. I think that will give you the right picture. And let's go down this way. Like this. I'm bad at these 3D drawings. So I hope you get the idea. It's sort of a spiral, right? If I draw it again, like just drawing the wire as a line, it would look something like this. It's just a spiral of wire. And you can have it wound up really tightly like this. Now, if you apply the right-hand rule to it, like the curly-hand rule to it, you try to figure out, okay, which, say the current, suppose the current goes like up this way and down this way, so it goes around like this. And you can sort of try, if you go along each individual loop, what kind of field do I get, right? What you're going to get is a field that it looks, if we draw it on this one, looks something like this. And then it sort of curves around over here. It sort of looks like a bar magnet a little bit, like a lot actually. And we suppose there's a total current I running up the wire. And then down this side. So the field, I'm going to use this drawing now, where I can sort of see inside because I made my wire thinner. The field inside is approximately constant. It's not quite true at the edges, you only get near the end of it, but I imagine the solenoid to be fairly long, more windings than I've drawn. So say it has n windings. And the field is approximately constant inside. Why? Because if you're a little point here, you don't know how much further the coil goes this way, the solenoid goes this way or this way. Like kind of, as far as you can see forward and backwards, you're in this tunnel of wire. So it looks the same whether you are here or here or here or here. So the field inside is constant, approximately. So if you get close to the edge, okay, not quite. But this is, am I doing this right? No. The field inside is approximately straight. B inside and approximately constant. Okay, so I want to find the field strength inside. That's my goal. So how are we gonna figure this one out? So I want to use my Amperian loop. Let me draw it again, this situation, just so to make my life a bit easier maybe. So here we go again. Like this. And the field inside is constant. And only when I get to the edge does it start bending outwards. So Here we go. So I'm going to pick my loop to go through the coil, and I'm going to, there are two choices here. You can make it either say you're going to go inside, you cut in from the side, go through it and cut back out. But I'm just going to go to the whole loop. So I'm just going to go along a field line through there, to the whole thing. I'm going to make it my loop. And then I'm going to do some funny stuff out here. Who cares? Nobody cares. I'm going back here. Right, so that's my loop. I'm going to go around the loop in the same direction as the field lines. My Amperian loop. Alright, so let's work this out. We assume my coil has a length L and it has N windings, right? So I wrote down up here, N windings, length L. So outside here, the magnetic field is very weak compared to inside, right? The lines spread out. There isn't much field, a little bit, sure, but not very much. So outside, B is very small. I know this because if I imagine this being fairly tightly wound, there's lots of field inside, but it's so spread out, means the field lines are less dense, means it's very weak. So I'm going to ignore the contribution to this loop on the outside. Very small. The outside part of the path, the integral log of this, is approximately 0. Not quite true, but who cares about details? What about the inside? Inside, I have that B dot ds, the inside path, is equal to, well, the B field is constant, so I can take it out. So the angle is 0. So this is just the strength of B times the length of S. Now the B field is because they're in the same direction, right? The angle is 0 between them, so the cosine factor goes away. Cosine of 0 is 1. And then this is going to be equal to, I can take B out. And I realize I'm squeezing this in here, which is now a bad choice with hindsight, but almost done. Times the length of the S inside. But this is of course just L. Right, so this inside path is just the field strength inside times L, because adding the step size from here to here just gives me back the length of the solenoid. So we've got B times L plus 0. That's my total loop. So I figured out the left-hand side in this case of Ampere's law, and the left-hand side is equal to B times L. That's it. What's the right-hand side? It's a bit more complicated, right? It's mu times the current inside. What's the current inside our loop? Now let's get to think in 3D a bit. You notice that the current that goes through it, it's always going under, which means the current is always in the same direction. It always curls around, but the curling around, the current that's going back is out. It's not going through the loop, right? So the current is coming through once, twice, 3, 4, 5, 6, and so on. So it's just the number of windings times the current through the actual wire, right? Because for each winding, the current's passing through our Amperian loop once, and yes, that counts. Mu naught times N times I. And so this is this. So I get that my magnetic field strength inside is equal to solenoid is equal to mu naught times N over L, like the L goes to the other side, times I. That is N over L. Why did I write it like this? Because that essentially tells me how tightly my solenoid is wound. This is my windings per length. Right? So it doesn't depend on how long it is or how many windings it has. It depends on the magnetic field strength, depends on how tightly they are together. Like 10 per centimeter is the same as 1,000 per meter. So the total length doesn't, if I have a coil and I just extend it longer, it doesn't change the field strength inside it. What matters is how close are those windings together. How many windings do I have per length? So it was another expression that you've met before, kind of just as a statement, the magnetic field strength inside a solenoid. Now we've proved it using Ampere's law. There are other examples. There are some more interesting examples. And one more interesting example, for example, is imagine you've got a wire that's actually a size, it's not like a single sort of thin line, and you ask, what is the field strength inside the wire? In that case, of course, we're going to pick our Amperian loop to be this, and now it works the same as for the normal wire, single wire, except the current inside is just the current going through here. So you're going to deal with current density. Another fun example to think about: what is the magnetic field strength inside a wire of radius r if your distance from the center is essentially less than the radius of the wire, so you are inside it. What is the magnetic field here? Fun to think about. I'm not going to do it for you. You can do it yourself. This video is long enough. I hope you learned something. The rest is just applying it over and over until you get good at it. Of course, doing so thoughtfully and reflecting on your own understanding is going to help, as always. Now, there's another little mystery before I finish. And the mystery is, what does it mean for current to go through a loop? Let me give you an example. Imagine my Amperian loop. This is really just sort of looking ahead a bit. I'll come back to it later. Imagine this is my loop. Imagine there's a current that comes this way. And it goes in here. Say this part here, this is kind of the front of the loop. It's just closer to us. And then the back side here. It goes in, it decided to change its mind, and it goes back out. Has it gone through the loop? Now you might say, well, I can imagine there's a sort of sheet that spans the loop, and if it cuts through the sheet, then it has gone through. Now in this case, it actually won't matter, because the current that goes through the loop is going to be zero, because either it hasn't quite gone through the loop, or if it goes through, then it goes back out, and so that the net current is zero. As much current goes one way as goes the other way. The mystery arises is if the following happens. Imagine, again, I've got a loop like this. Again, I'm going to imagine in 3D that this side on the left on the paper, side I've drawn a bit thicker, is in front, and this side is further away. Now imagine the current does this. It comes here, and then it stops. Now wait, you say, how can a current just stop? Where do the charges go? Yes, the charges will be building up here. One situation you might imagine is if somebody put it like a sort of capacitor here, and the other side of the capacitor is over there, so kind of make a loop through, like around here, so that just the end of the capacitor sticks out through that loop. Is the current going through the loop? Maybe. it's hard to know, right? The loop might, like the way what it means for a current to go through a loop, the way we think about it is that we imagine there's a sort of a sheet that spans the loop. Now you could pick any sheet you want. You could pick a sheet that's like this, a sort of you know, butterfly net, let's call it that, if this is my loop. Then any current that goes in here, it hasn't gone through the loop yet, but eventually it'll have to go through there. So in our loop becomes the edge of an open surface. And now you can see this situation more clearly too. If I take this open surface here, that's just a sort of circular, the sort of the thing you would naturally pick as your surface if this was your loop. Okay, this one might cut through and go back, whereas for this one here, the butterfly net, it'll come in, go back, and never cut through the surface. But that's okay, because in both cases the net current is zero. The mystery arises if the current comes in this situation here, and then there's a capacitor, one plate inside your butterfly net, the other one is outside. Now current, if it's the butterfly net, no current goes in, no current passes through it. But if I pick the sort of basic covering of the basic surface, the current does pass through it. So how do I apply Ampere's law here? And that actually creates a little bit of a mystery that's only resolved when we do a little correction to Ampere's law. But that is the story of some future.